we're gonna go into page 2 real quick, if my computer will load, hopefully. The thing about this is that it's better for me to go to Desmos and do this stuff, mainly because if you think about it, numerics, you can't really, yeah, you can write it by hand, but what's the point of doing that sometimes? So I do want to show by actually do it in some online capacity. Basically go into Desmos and do it. Last time, I believe we finished. Oh, I forgot to give credit. Let me quickly give credit. So all credit goes to these people. We have. And we start with our classical definition over here, which is a mesh that leads I believe what they call it, I forgot. But yeah. Why is my tablet not moving? It should move to it should follow. Stop following. Follow. Okay, here we go. So what's trying to say was when we start Taylor series, we're notified usually about this fact over here. So we'll start over here, right? Taylor series, any function you put in here, we start with a function, and then we have it evaluate a certain point, right? And you don't know how this Taylor series would work, so you want to what's the right word? Expand it, right? And the expansion is basically a bunch of derivatives in turn, getting you a certain answer. And if I remember correctly, I should really have it in my head, honestly. Been using it for forever. And I believe, yes. So it is summation of n, k equals 0. I'm switching it up. Fk, xo, and then ki, x minus x0, k. And there's a remainder here that you can, if they actually care about that stuff. I don't think they do. So they rearrange it. So this is a basic one, which is by expanding this, you see that fxj plus 1, right, equals fxj, which is true. If you think about it, so what's going on here? Well, it doesn't make sense first what's happening, actually. So let me explain before I continue on here. So first thing you need to figure out is what is xo. Xo is xj in this situation, because you're jumping off of a point. Basically, what's happening is you decide the initial condition and you're expanding the rest out from that initial condition. So whatever is in the initial condition, you are propagating it outwards. And that is basically my understanding of Taylor series with the continuity and other stuff. This is why if the function isn't really defined in a particular way, you can kind of see a region where Taylor series works. Like from this point, if you start from here, and let's just say if all of a sudden it goes down like this, you have no idea why, that is because you're propagating out from that point and building up this function. Now, certain functions may have some problems with that, which causes this mess that I'm displaying here. That is my understanding of Taylor series, xj. And what's happening here is spanning this out. And then plus xj plus 1 minus xj, and then so on and so forth. But we don't need anything beyond this point because we're going to do order of, I believe they tell you what order this is. They don't? They should. I think it's x to the square. Pretty sure I'm pretty sure that it's true, but I can't really determine yet. Okay, whatever. But we'll figure it out. I think it's something like that. And what you have to do is move this out. So what's happening is saying over here, move it this way. It's saying fxj plus 1 minus fxj, and you divide it by xj plus 1 minus xj. That equals f prime, and this equals to, oh yeah, I know why I made a mistake. It's order of xj plus 1 minus xj square, and then this is divided by the order of xj, so on and so forth, which makes an order of order of delta 1. So over here is in a way that makes sense. Yes, right? No, yes, does that make sense? It probably doesn't. What's basically saying is that if you have some data points over here, you can figure out the derivative by doing this kind of stunt. And by figuring out the derivative right here, you can what can you get from that? You can get the direction of movement and you can move towards it and you can do some kind of funky stuff. Why does that work? Is think about how we operate. We operate with initial conditions. If we have an ODE, we operate with the idea there's initial conditions that make you propagate throughout. So similarly, Taylor series is the same way, right? It starts with the initial condition and you propagate outwards. And in my opinion, that's why it works. But that's just my opinion. If I might be totally yapping on nonsense, but that's my understanding of how finite differencing works. It's the idea that it propagates outwards, but you can they or Taylor Swift is anything else. And yeah, the funny thing is that beyond that point, there's like a fourth order version with central defining and all the math. But in reality, we stick with first order often, and that is due to a lot of times with CFDs, anything beyond first order and for finite differencing, for central differencing, second order is fucking useless. Don't go beyond it. It's like wasting your fucking breath. That taught me things because he did teach me this. Give credit to this man over here because he did teach me this. Let me go over here. Yeah, it's not working. Why? It's because of all these nodes. Next. Oh, come on, not loading. Well, there's another way to do it. And actually, this is cheating it, but you can do it this way too. You can actually just say, index, right? Index -2 here, and index over here -2 here, and you get the same thing. I say -1. I don't remember, but it's a way to get it, I believe. I think it's -1. Yeah, -1. Yeah, it's a way to get it. Actually, I think that's the way he did it. Yeah, I think that's what he did. Actually, not thinking about that's what he did.